In all of the earlier videos in this module, we've been looking at propositions, complete statements that have a definite and knowable truth value. We've seen lots of examples of propositions and learned how to work with them. In this video, we're going to reintroduce an earlier example of something that wasn't a proposition. And here is that example, x plus 5 equals 12. This is a kind of a statement, namely it's an assertion that the expression on the left side of the equal sign, x plus 5, is actually equal to the number 12 on the right. So it's a complete thought, but it's not a proposition because it doesn't have a definite truth value as it is, because of that variable x. Whether this statement x plus 5 equals 12 is true or not depends on the value of that variable. If x equals 10, for instance, then the statement x plus 5 equals 12 is false. But if x equals 7, the statement is true. We're going to call a complete statement whose truth value depends on the value of one or more particular variables a predicate. Predicates are different from propositions. While both predicates and propositions have truth values, the truth value of a proposition can be known just from the proposition itself without any outside input, while the truth value of a predicate depends on outside input. Propositions have only one truth value, while in general the truth value of a predicate will be true for some inputs and false for others. It depends. For notation, while we often use letters like P, Q, or R to represent propositions, we'll affix a variable in parentheses to a letter to indicate a predicate. For example, we could write this to mean the predicate, called P, with variable x, is the statement that x plus 5 equals 12. We pronounce this first part here P of x. The allowable inputs for a variable and a predicate is called the domain of the predicate. For example, for P of x here, the domain could be all real numbers. But here's another predicate. Q of x is the statement x mod 3 equals 0. And for this predicate, not all real numbers might make sense. Instead, the domain is a set of integers, because that's the only thing we can apply the modulus operator to. Some predicates might have even smaller domains. For example, this predicate, B of x, is the statement Professor X has a beard. Apparently, x represents not a number, but a faculty member, and since there are a lot of faculty members out there, we might just explicitly state that the domain here, for example, is the set of all mathematics professors at your university. More formally, we can say that a predicate is a function whose domain is a given set and whose codomain is the set true-false. This is using some language we haven't defined yet, but we'll be doing that in the next module. It just means that a predicate is like a machine that accepts inputs from a given collection, performs some kind of process, and produces outputs of either true or false. Predicates are extremely important and useful in computer science, not least because they themselves are like tiny computer programs with an input of a certain type and which output either true or false. Here, for example, is a Python version of our first predicate. You plug in a real number for x, then go through a process to return either true or false. Let's look at some more examples of predicates. S of x is the statement, the length of x is 7. Where x is a string and the domain is a set of all possible strings. Again, it's helpful to think of this like a little computer program, like this, where you plug in a string, do a process, and get out either true or false. The predicate itself does not have a truth value until something is plugged in. For example, S of mathematics is false because the length of that string is 11, but S of algebra is true because the length of the word algebra is 7. Here's another example. P of x is the statement x squared is bigger than 0, where x comes from the set of all integers. P of x will return a true whenever x squared is bigger than 0 or equal to 0, and a false otherwise. So P of 2 is true, for instance, because 2 squared is 4, and that's bigger than 0. P of 10 is also true, because 10 squared is 100, and that's bigger than 0. In fact, P of x is always true for any input, because squaring an integer always returns as a result that is non-negative. And another example, P of S is the statement the length of S is negative, where the domain is all possible strings. Well, this predicate is never true because there's no such thing as a string with a negative length. Generally speaking, we can have predicates that are sometimes, but not always true, predicates that are always true, and predicates that are never true. When we talk about how often a predicate is true, this is referred to as quantifying the predicate, and our next video is going to be all about that idea. We can even have predicates with more than one variable, like this. P of x, y is the statement x times y is bigger than 0. This requires knowledge of two variables to be able to determine truth. P of 2, 3, for example, is true because 2 times 3 is 6, which is bigger than 0. But P of negative 4, 5 is false because negative 4 times 5 is negative 20, which is not bigger than 0. Now you give it a try. Here's a predicate. P of n is the statement 3n plus 1 mod 4 is 0. Pause the video now and find as many values of n as you can that make this predicate true. Come on back when you're ready. So I've actually written a Python function here to help me find these. The predicate is here in this first block. It just implements the process of returning true if 3n plus 1 mod 4 is 0 and false otherwise. Now down below, I'm going to run a quick loop to go through the integers 1 through 30 to see which values in that range make this statement true, and hopefully I will see a pattern. So it looks like 1, 5, 9, 13, 17, 21. I believe I'm seeing a pattern here that whenever n itself is congruent to 1 mod 4, the predicate will be true. I'll test that out with some integers outside the range we just saw. For example, a negative integer, like negative 3. That's congruent to 1 mod 4, and sure enough, my predicate is true. Or 400,001 is 1 mod 4, and that also gives true. So while I can't literally list all of the values that make the predicate true, I can put them together in one place and indicate a pattern like so. This collection, consisting of all the variable values that make the predicate true, is called the truth set of the predicate. For example, for the predicate P of x being the statement x plus 5 equals 12, the truth set is just the single number 7. For P of x being the predicate x squared is bigger than or equal to 0, the truth set is the entire domain, the entire set of integers. And for S of x being the statement the length of x is 7, the truth set is just the collection of all strings that have length 7. So you've learned a lot in this video, the differences between a predicate and a proposition, the domain of a predicate, and the truth set of a predicate. In the next video, we'll come back to this idea of quantifying a predicate that we mentioned earlier. That's taking a predicate and turning it into a proposition by making an assertion about how often the predicate is true.